In problem number 10 on the homework, we're being asked to calculate a line integral. We are given a potential function, x plus y plus z, and we want to integrate it over the curve, which is given here as a circle given by r of t equals 12 cosine t, 0, 12 sine t. So it's a circle in the xz plane because the y coordinate stays 0 the whole entire time. And it's for t from 0 to 3 pi over 2. The ds means that we not only have to worry about how the t values are changing, we need to worry about how the curve in general is changing. The shape of this curve is going to have a lot to do also with the value for the line integral. So the particular formula that we're going to use for this one is when we're given an integral around c, so a line integral for f of xyz. This is a little f because it's written out as a single function of multivariables. It's not the capital F, which is a vector field. It would be given to you as a vector. So we're given an f and we're asked to calculate ds. S here stands for arc length. So I want to just explain to you really quickly how I'm going to convert this into a more usable form, because we don't have a function in terms of arc length, we have a function in terms of time. So arc length, I think from a couple chapters ago, if we're talking about the curve r of t equals x of t, y of t, z of t, and I want to know the arc length for that curve from t values a to b. Arc length is the integral of r prime of t magnitude dt from a to b. That's how we figure out the length of that curve. Well, if we do a little bit of calculus on this, and in particular, I'm going to take the derivative with respect to t, we get ds dt equals, well, when I differentiate an integral, and they're both with respect to the same variable dt, they really just cancel all each other out, and we're left with r prime of t, the magnitude. We're trying to figure out what to replace ds with. So I'm going to solve here for ds by multiplying that dt over. So we're going to replace ds with magnitude of r prime of t dt. That's going to be very helpful because the information that we have given right now is r of t. We have a function in terms of x, y, z that we want to integrate over. But we can't mix x, y's, and z's with t's. But what our vector valued function gives us here is a representation for x, y, and z in terms of t. So when the line integral is given to us in this format, really what we're going to do is integrate from a to b. We're going to write f using the x of t, y of t, z of t given to us in the r of t. And the ds is going to get replaced with this guy, which is magnitude r prime of t dt. So this is exactly what we need to calculate. And it's just a single integral. So once we get it all set up, it's actually pretty easy. It's all this work ahead of time, really, in understanding what's going on and how to convert it into a more calculatable form. That usually is the trickier part. So let's go ahead and actually calculate this guy. So I'm just going to copy the problem down here. So there's a couple things that we need to do. We have, we have this f function here currently in terms of x, y, and z. So what we're going to use is our r of t components to replace them. So this is going to turn into x plus y plus z is going to be 12 cosine t plus 0 plus 12 sine t. And we can leave the 0 off. ds, remember, is going to be magnitude r prime of t dt. So up ahead here, I'm just going to figure out our r prime is going to be negative 12 sine t, 0, 12 cosine t. And we want just the magnitude for that. So we're going to add together the components squared under a square root. Negative 12, be really careful. This is a common mistake. When you square a negative, it always turns into a positive. But if you don't know that and you type them into the calculator in the wrong order, it might come out as a negative. So just keep it in mind. Anytime you square something, it should come out positive. So 144 sine squared t plus 0 squared, so I'm just going to leave it off, plus 144 cosine squared t, which can be simplified because sine squared t plus cosine squared t is a Pythagorean identity for 1. And we could get those two guys together if we factored out the 144. Then this is just equal to 1, and we really just have the square root of 144, which is 12, and dt. And our t values were 0 to 3 pi over 2. 12 cosine t plus 12 sine t times 12 dt. Now this is the integral that we need to solve. So I've got a 12 here in common inside the parentheses. If I factor it out and combine it with the 12 outside, that will give me a 144 in front. And then we're just integrating cosine t plus sine t dt, which is the antiderivative is going to be sine t minus cosine t. And we want to evaluate at 3 pi over 2 and get an answer. And then we want to evaluate at 0, get an answer, and then we'll subtract. So first, when we plug in 3 pi over 2 for the t's, I get 144. Sine at 3 pi over 2 is negative 1. Cosine at 3 pi over 2 is 0. And then we need to subtract what we get when we plug in 0. Sine of 0 is 0. Cosine of 0 is 1. And there's a subtraction there. So we've got negative 1 minus 0. That's negative 1 times 144 is negative 144. And then over here I've got 0 minus 1, which is negative 1. So I'm going to have a double negative here. It's going to turn into plus 144, and we get an answer of 0. Seems like an awful lot of work there to just get all the way down to an answer of 0, but that's correct. Number 11 in the homework is given to us in a very different format. It says, given the force field F, find the work required to move an object on the given oriented curve. And they give us F is the vector field with components y comma x. And the curve is the parabola y equals 6x squared from 0, 0 to 496. So this one also is a line integral, but it's being asked in a different way, and it's giving us a different set of information. First and foremost, we are going to have to parameterize that curve ourselves. The easiest way to parameterize a curve, especially if it's an algebraic, which means no trigonometry. If it's an algebraic curve, all you have to do is let x equal t, and then plug that back in and get what y is equal to. Well, if x is equal to t, then y is equal to 6t squared. And the t value here is the first one. It goes from 0 to 4. And you should check to make sure that the y matches up as well. If my t goes from 0 to 4 and y is equal to 6t squared, it will start at 0, so that's correct, 0, 0. And 4 squared is 16 times 6 more is 96. Yep, so perfect. This means r of t is going to equal t comma 6t squared. The F in this case is a force field, and they're specifically asking us for work. So one of the things you might remember either from physics or calculus 2 is that work is equal to force times distance. But if that force is a variable force like we have here, we need to think of it as an integral of F dot dr. dr we could easily calculate because we now know what r is equal to. Our r function is written in terms of t's. So the dr is going to have t's in it. We're also going to want our f function to have t's in it, and that just means we need to use x of t equals t, y of t equals 6t squared to rewrite our force field. And then because these are both vectors, it's not just an algebraic multiplication, it's going to be a dot product. So we know that r of t is equal to, I'm going to write this with i's and j's, ti plus 6t squared j. If we take the derivative of both sides with respect to t, we get that dr dt is equal to 1i plus 12, if we bring the 2 out, tj. And then we're going to multiply that dt over. So dr is equal to 1i plus 12tj dt, which means we can replace this dr right here with this stuff. And we don't want to do that dot product until these two pieces are written in terms of the same variable, which is going to be t. So my f, which currently is defined as y comma x, needs to be, those two components need to be replaced with what they are equal to in terms of t in our curve. So in our curve, the y value, remember, is 6t squared. The x value is just t. So I now have both f and dr in vector format. And inside that integral is going to be f dot dr. So the integral of f dot dr is equal to, dr is going to get replaced with all this stuff, and we need to dot it with f. So dot product means multiply corresponding components. 6t squared times 1 is 6t squared. And remember, dot product, the answer for a dot product is a scalar. We don't separate the answer with i's and j's. We add those two products together. So now if we multiply our j components, we have 12t times t, which is 12t squared. And we have dt. The t values we said earlier came from doing our parameterization. It was for t goes from 0 to 4. Well, if I were you, I'd go ahead and add these together before we integrate That is actually 18t squared from 0 to 4. So antiderivative is going to be 6t cubed from 0 to 4. Plug in your top number first. So we've got to calculate 6 times 4 cubed. And then subtract what you get when you plug in the bottom number, which is just going to be 0. 4 cubed is 64. So we've got 6 times 64 here, which is 360 and 24, so 384. We were not given units for the F and the DR. We just know that this is work. It very well could be joules or anything, but we're not real concerned about that, but it's 384. I would also strongly encourage you to take a look at number 7 from your homework when you have some time to study for your final exam. 7 is something you might see. And this one's a little bit different than number 10 and number 11. And it starts off looking like number 10, where we've got a function of x and y, and then we've got this curve we want to integrate over. So this is very similar to how number 10 was presented to us, but be careful because we're told that the path is r of s. And what that means is we don't need to include the magnitude r prime piece. Back at number 10, the only reason we needed that magnitude r prime piece was so that we can change the ds to a dt, because everything was in terms of t. Here, we don't need to change the ds into anything because everything is in terms of s. So this is like one of the simplest problems we could be asked to do. All we have to do is change the x and y to be in terms of s using these guys here. So if we do the x component times the y component, we're going to be integrating cosine of s times sine of s, and then ds, and this is for s on the integral from 0 to pi over 2. Now, in order to integrate this, you're going to have to use u substitution. So I'm going to let u equal sine of s. Take the derivative of both sides. That would give you du equals cosine s ds, which is perfect because sine s is u, cosine s ds is du. So it just simplifies all the way down to the integral of u du, which is 1/2 u squared. And we can't plug those values back in until we're back in terms of s, because those are s values. So we'll go back, now that we've done our antiderivative, we'll go back and plug in what u is equal to. So we've got 1/2 sine squared s from 0 to pi over 2. Sine at pi over 2 is equal to 1, and we're being asked to square that and multiply by 1/2. Sine at 0 is 0, and we're being asked to square that and multiply by 1/2. And this just ends up 0. 1 squared is equal to 1 times 1/2 is a 1/2. So this one's actually really easy. It's like number 7 in your homework. All we have to do, since our path is already in terms of s, is just plug in our x and y's in the correct spot and integrate. One last problem that I would like you to look at is in the textbook, section 17.2, number 35. So we've got a thin wire represented by the smooth curve C with a density rho, which is in units of mass per length. To calculate the mass of that wire, what we have to do is integrate our density function over that curve that actually represents its position through space. So we want to find the mass of the curve with these values. So all this is a line integral. The c is given as a function of x and y. In number 10, either number 10 or number 11, we had to parameterize that ourselves. I think it was number 11. So we've done that before. We can find a parameterization. And then rho is 5 plus xy. So we would just want to write rho also in terms of our parameter t. And then we'd have to change ds to dt. So we'd probably have to work out one of those little derivative formulas to see how those would switch with each other. So let's jump into it. We first need to parameterize that curve. So the easiest way to do that, remember, is just let x equal t and plug it back in, and then you get y is equal to 3t squared. X goes from 0 to 5, and for us, we said x is equal to t. So this is going to be on t from 0 to 5. And if you want to, you can write that as a path or a vector valued function. We've got components t and 3t squared. We then need to write our rho function, our density function, in terms of t. Right now, density is 5 plus xy. We're going to replace x and y with what their values here are in RFT, or also what they are over there. So we've got 5 plus, well, if we multiply those together, we're going to have 3t cubed. So we're being asked for the integral of the rho function, which is 5 plus 3t cubed. We know that t is varying from 0 to 5, but one thing we have not addressed right now is the ds. So now we need to remember, I'm not going to write it all out again, but back when we did number 10, we were able to figure out that ds is equal to the magnitude of r prime of t dt, which is perfect. We want to integrate with respect to t, and in order to switch out the ds with the dt, we just have to throw in a magnitude of r prime in there. So we're still integrating from 0 to 5. Our density function, which is 5 plus 3t cubed, but now we need to multiply by magnitude of r prime of t. So r prime of t up here under the r of t is, we're taking the derivative, so 1 and 6t. And then the magnitude of that is going to be them squared and added together under a square root. So 1 squared is 1, and 6t squared is 36 t squared. And then dt. This is not one that I would suggest you try to work out by hand. Like I said before at the very beginning, sometimes the hardest part is just getting this integral set up. Once you get the integral set up, it's pretty straightforward from there. It's like a calculus 1 single variable integration problem. So I am not necessarily interested in you having to work out all those crazy calculus 2 techniques of integration. Since this is a definite integral, just type it in your calculator. Just be very, very careful that you type it in with all the proper parentheses and stuff so that it is equal to, that you actually get the correct answer. So I've typed this into my calculator, and I am getting approximately 11,637.32266. Now, another thing I want to point out before you guys take your final exam, in blue, underneath every single MyLabs Plus problem, there are specific directions on how you need to type your answer in the box. This one says round to 1 decimal place. Don't worry about the as needed. That just means it might not have a decimal place. We're only interested in fixing the ones that have more than 1 decimal place. So we only want to keep 1 decimal place. That means we're going to look to this one to decide whether the 3 is going to stay the same or whether we should round it up to a 4. So since this value is less than 5, that tells me my 3 stays exactly the same, and I can just ignore that stuff. So 11,637 and 3/10, or 0.3.